Hello everyone, this lecture is on rotations in 3D. So in lecture 2.2, we developed the rotation matrix in 2 dimensions, and now we're just going to extend it to the 3rd dimension. And all the properties we derived for the special orthogonal group still apply here. So in the previous lecture 2.2, we looked at a rotation matrix in the XY plane. And now we're just going to extend it up with the 3rd dimension in the Z. Right, so we just add a 3rd dimension to this rotation matrix. And now we have our rotation matrix with unit vectors in X, Y, and Z. And we say that this is in the special orthogonal group in 3 dimensions. So each column of this rotation matrix is a 3D unit vector, so that X hat, Y hat, Z hat are in the set of real values in 3 dimensions. And the norm of each of these vectors is 1 because they're unit vectors. And again, we say that all of these columns are orthonormal, meaning that they're orthogonal to each other and that their magnitude is 1. So if we take the transpose of each vector on another column vector, then we end up with 0. So they're at 90 degrees to each other. So now in order to discuss orientation in 3 dimensions, we need to consider the right hand rule. So taking our right hand and making the gesture like in the diagram here, then we have x-axis forward from the index finger, y-axis left from the middle finger, and the z-axis up from the thumb. And then we can define a roll angle phi about the x-axis, like so, a pitch angle theta about the y-axis, like so, and a yaw angle psi about the z-axis in this direction. So now that we have the right-hand rule and 3 axes, we can define elementary rotations about each of these unit vectors. So a rotation purely about the x-axis is given by this matrix here. And notice that the row and column associated with x are empty. And what this means is that the x-axis remains unchanged. Similarly, we have a pitch angle theta given by this matrix here and as shown in the diagram. And you will notice that the row and column vector associated with the y direction are empty, meaning that any vectors along the y-axis remain unchanged. And lastly, we have a rotation psi about the z-axis given by this matrix. And again, the row and column associated with z is empty. So any vector pointing in the z direction will remain unchanged. And you will recognize that this 2x2 block here was simply the rotation matrix we developed in 2 dimensions. That is rotation along the xy plane. So we can make combinations of these elementary rotations. So a rotation matrix can be formed from a maximum of 3 sequential rotations about the primary axes. That is, we have the rotation matrix as a function of phi, theta, and psi. These rotations can be in any sequence, but not in the same axis in succession, because if we just take a rotation about x twice, then this is just 2 phi. So this is redundant information. In total, there are 3x2x2, which equals 12 combinations of these rotations. So the first group are called Euler angles, and this is when we rotate about the same axis twice. And there will be 6 combinations of these. So the rotation sequences highlighted in red are the Euler angles, and you'll notice that the first and last of each of these is about the same axis. So we have xyx, xzx, yxy, yzy, and so forth. So the first and last rotation about the same axis. The next group are called the Cardan angles, and this is when we rotate about all 3 axes. And again, there are 6 combinations of these. So the ones highlighted in red here are the Cardan angle rotations, and you'll notice that we have each axis represented. So xyz or xzy, zyx. So each of the axes in different combinations. One thing to consider is that order of rotations is extremely important. So if I rotate about x, y, and z, this is not the same as rotating about z, y, then x. So if I have this reference frame here and I rotate about x, y, then z, I will end up in this orientation. But if I take this original reference frame and rotate about z, y, then x, I will end up in this rotation. So it's totally different. So this is because matrices are not commutative. And we can prove this quite easily. So if I take the inverse of AB, this will be inverse of B times the inverse of A. And then if I multiply AB by the inverse of AB, what I have is A times B times inverse A. And this will be the identity matrix. And we're left with A times inverse A. And again, this forms the identity matrix. But if I take B times A by inverse of AB, what I have is this. And we can see that these two matrices will not cancel each other out. And this is not the identity. And therefore, A times B is not B times A. So rotation matrices are still matrices, and these rules still apply. So consider that we have a rotation matrix that was formed from a rotation about phi, theta, psi, each of the x, y, z axes, given by this 3 by 3 matrix here. Then we can extract the phi angle with this function, a tan 2 of r32 and r33. So r32 and r33. We can extract psi, the rotation about z, given by a tan 2 of r21 and r11. And then we can extract the rotation about the y-axis theta with this conditional equations here. So either we have R31, R21, or R11. So given a rotation matrix, we can always go back to the roll, pitch, and yaw angles. So one thing we need to consider when working with roll, pitch, yaw angles is the problem of gimbal lock. So if I take a reference frame and rotate it about theta equals pi on 2, as shown here, then I have this rotation matrix. And I can multiply this by starting with a rotation about x, phi, then theta by pi on 2, and then z by psi, which solving down to these two matrices, and then to this final rotation matrix. Right, so we rotated about the y-axis by pi on 2, and this rotation about x, y, and z with the y defined by pi on 2 gave this rotation matrix. And if we look carefully, we can see that from trigonometry that we can reduce this down to this function here, where we have sine phi plus psi, cos phi plus psi, negative cos phi plus psi, and sine phi plus psi. And what this means is that when the pitch angle is plus minus pi on 2, the roll angle phi cannot be distinguished from the yaw angle psi. So this is a big problem. We've lost a sense of direction with our orientation. So let's look at an example. If I have a rotation by phi theta psi defined by a rotation about x by 4 pi on 7, rotation about y by pi on 2, and a rotation about z by negative pi on 3, what I have is this rotation matrix here. And then if I extract the roll, pitch, yaw angles as I previously defined, then my phi, theta, and psi angle will now be pi on 2, 0.97, and pi on 2. So you can see that this is not the same at all. And this is the gimbal lock problem. So even with my original definition, now I can't extract what my original orientation was. So what we have to do is either set the standard operating conditions of our robot away from theta equals plus minus pi on 2, or we just avoid maneuvers that pass through theta equals plus minus pi on 2. So we can define a rotation error as r subscript e by r subscript d by r transposed, where here rd is the desired rotation that we want to be at, and r is the actual rotation. And so what this means is that the rotation error is the identity, then the desired rotation equals the actual rotation, because we know that R times R transposed will give the identity matrix. So let's suppose that we have the rotation error calculated with this 3 by 3 matrix here for any given values of the elements. Then we can extract the roll pitch yaw angles from the rotation error. So phi, psi, and theta. So therefore we can define the error in terms of the roll pitch yaw angles. So to summarize rotations in 3D, we have the right-hand rule used to denote axes and directions of rotation. A rotation can be constructed from rotations about the primary axes, that is Rx by phi, Ry by theta, and Rz by psi. And order of rotations is important because matrices are not commutative. And a gimbal lock occurs when the pitch angle is 90 degrees, and therefore we cannot distinguish phi from psi. And the rotation error is defined by the desired rotation by the actual rotation transposed.